This is Derf Sites. This functions tutorial is about polynomial functions. A polynomial function in standard form is shown here. P of x is a sub n, x to the nth power, plus a sub n minus 1, x to the n minus 1 power, etc., all the way down to a sub 1, x to the first power, the linear term, plus the constant a sub 0, where the exponent of the leading term is a whole number. The coefficients, the a sub n's, may be real or non-real complex numbers, and the leading coefficient here, a sub n, is not 0. The degree of a polynomial is the degree of its leading term. For this general form, this standard form here, the degree is n. Visual properties of polynomial functions. Polynomials are continuous and smooth. Look at this example here. Continuous, if you look at the graph of the polynomial, it is unbroken. There are no breaks in it. If you were drawing it, you would not have to lift your pen off the drawing surface. These ends here keep going up, and this one keeps going down. But there are no gaps in it, no breaks in it. That's the meaning of being continuous. Smooth means there's no abrupt, sharp corners. They're very smooth. This one down here looks like it might be sharp, but it's just the zoom level. If we were to zoom in to get closer and closer to this area here, we'd see that it is curved, and if we got close enough, we could make it widely curved and even appearing as almost a straight line down there. And this particular polynomial here is a 7th degree polynomial. Continuous and smooth. Let's look at the end zone behavior of polynomials. What does it mean, the end zone behavior? That means when the value of x is approaching negative infinity on the left or positive infinity on the right, what will the value of the polynomial approach in those end zones? To understand this, let's consider an analogy of the sun, the earth, and the moon. Here we have a picture of the sun, and over here a picture of the earth as a little blue dot, and next to it the moon is a little white dot. Of course, you could not really look at the sun because it would be so bright, but in this picture it's sort of dulled down so you can look at it, but picture it in its brightness. If you were in a distant galaxy, far, far away, looking at our star, the sun, how much of the light that you see would come from the Earth's moon? It's virtually zero. The sun dominates entirely the light that you see. Similarly, the leading power function of a polynomial, a sub n x to the n, because it has the highest exponent, dominates the value of the polynomial for very large values of x, whether positive or negative. Let's look at even degrees for the leading term. If it was x squared, it would look like x squared here, and all the even powers look similar to x squared. As you go to the left and you go to the right, the values go up and up. If you take minus x squared, the values go down and down. Those are even degree leading terms. If the leading term is an odd degree, the behavior is similar to x to the third. Here, this blue one, here's x to the third. As you go to the left, it's down, and to the right, it goes up. Whereas negative x to the third is up and down. This is summarized in this table with the degree here even in a leading sign positive or even negative, odd positive and odd negative. Those are the four cases. The left end zone and the right end zone. Up and up, down and down, down and up and down. And if you just remember that x squared and minus x squared and x to the third and minus x to the third are general patterns that all the other even and odds follow, you can remember this very simply. Let's discuss the meanings of these terms here: zeros, factors, and solutions. We know what factors are, and we know what solutions are. Zeros. A zero of a polynomial function, p of x, is a real or complex number. And when we say real or complex, we mean a real or a non-real complex. Just for shorthand, we just call it real or complex. So it's a real or complex number z such that p of z equals 0. When you substitute it in as the input to the polynomial, the output is 0. That's why it's called a zero. Z is also said to be a root or solution to the equation p of x equals 0. If z is real, then z is an x-intercept of the graph of p. Z is a zero if and only if x minus z, this linear term here, is a factor of p. If and only if. That means if z is a zero, then x minus z is a factor, and if x minus z is a factor, z is a zero. Every polynomial of degree n greater than or equal to 1 can be factored into the product of n linear factors. Here we show them with a leading coefficient of a sub n, x minus z1, x minus z2, where these constants, z sub I, may be real or complex. They are not necessarily distinct. There could be some repetitions, and they are the solutions to the equation p of x equals 0. So these are the zeros. They give us the solutions, and the linear factors here, n of them. Again, remember, some of them could repeat, not be distinct. If all the coefficients of p of x are real, and if a plus bi is a complex zero, then its conjugate, a minus bi, is also a zero. So complex zeros come in conjugate pairs. This area here, talking about the linear factors and the fact that there's n of them, comes from the fundamental theorem of algebra. Let's look at some examples. The following fourth degree polynomial function has 4 real zeros. Here's the function, and we're showing it in its factored form. Notice if we multiply this out, we would get a fourth degree polynomial because of the 4 x's involved in the 4 linear terms here. And by the zero factor property, we can see what the zeros are. Setting each of these factors equal to 0 and solving, we see that the zeros are at -2, -1, 1, and 2. And we right here, -1, 1, -2, -1, 1, and 2 indeed are where the graph crosses, in this case, intersects the x-axis, and the value of the function at those points is 0. The next example, here we have a 5th degree polynomial. It has 4 complex zeros and 1 real zero. Again, it's shown in factored form. If we multiply it out, it'll be a 5th degree. And this term right here gives us our real 0, setting that equal to 0. X is 2. These other two terms here, x squared plus 1 and x squared plus 2, setting those equal to 0 and solving, here we get x squared equals -1 using the square root property. We get x is plus or minus the square root of -1, and x is plus or minus I. And over here, x squared equals -2. X is plus or minus the square root of -2. X is equal to plus or minus the square root of 2 times I. So 4 complex zeros there. And we see that there's only one x-intercept corresponding to the real 0 at x equals 2. Talking more about intercepts, the y-intercept is when x is 0. So if you evaluate the polynomial at 0, in standard form, it's the constant term, a sub 0. And the x-intercepts are the real zeros. To find them, you factor the polynomial into its linear factors. Note that complex zeros are not x-intercepts. Here's an example. The y-intercept for this example is p evaluated at 0. If you substitute 0 for x, you get 0. And we see that it does cross the y-axis at 0. The x-intercepts use the zero factor property to solve. Here we have this x term here is the same as x minus 0. Setting that equal to 0, we get x equals 0. And 2x plus 1 equals 0 gives us a -1/2. And over here, x minus 2 equals 0 gives us 2. So 0, -1/2, and 2 are the x-intercepts, and they're the real zeros. Multiplicities. The multiplicity of a 0 is the number of times it appears as a linear factor. Multiplicities affect the behavior of the graph at the zeros. And this table summarizes this behavior. If the multiplicity is even, then the graph touches the x-axis at the 0 and turns back without crossing. If it's odd, the graph crosses the x-axis at the 0. And if the multiplicity is not equal to 1, regardless if it's even or odd, the graph will level off at the 0. looking at this example here, we have three linear factors. This first one, which has a 0 at -2, has a multiplicity of 1. Just appears one time. And it's odd, so it crosses the x-axis at the 0. And we see that it crosses over right there. The next 0 at -1 has a multiplicity of 2. So it turns around, touches and turns around at that 0. And the third 0 at 3 has a multiplicity of 3. So it crosses the x-axis, but since the multiplicity is not 1, at the 0 it levels out and then heads back up. So it's increasing all the time, but it's leveling out at the 0. Turning points. A turning point is a local maximum or minimum point on a graph. A polynomial of degree n has at most n-1 turning points. Here's a 6-degree polynomial function. It has 3 turning points. One right here, one here, and one here. Over here, this is not a turning point because it continues to increase. It's not a local minimum or a maximum. Approximation of a 0. Not of a 0, at a 0. If you have a polynomial function and you want to get an approximation function at a particular 0, then here's how you do it. In our example here, here's the polynomial, and we're going to approximate it at x equals -1. To do it, you substitute -1 for x. However, at the 0 itself, which is this linear term here, we do not put in the -1 because that would make it 0, and that would just be set the whole polynomial to 0. Not a very interesting result. So we leave x at that point, but put -1 for everything else. And then as we simplify after substituting, we end up with -16/5 x plus 1 squared. And you can see it's this red parabola here, and it is a very obviously good approximation, a simpler function, an approximating function at that 0. This concludes this tutorial on polynomial functions.